So master sets or chapter 8. Maybe this is how you do 2-week courses or 8-week courses.
As far as the test, I mean, it's pretty much just like force diagrams and.
Facades.
Okay.
Yeah. Chapter 6 brings in circular motion,
Okay.
like constant speed circular motion. All right, so momentum. Master set 8. Is that due today, or is that I changed that to Thursday? No, Monday, Tuesday next week. Sometime in the future. Are people well versed in those videos? Is all what I can skip.
I just finished chapter 7.
Newton's third law, shorthand conversion. As established, the two objects interact. In the example that we did earlier, it's while they were actually touching, but this works for any two objects exerting a force on each other. There's a force between the Earth and me. We will exert a force on each other for the same amount of time. And so I can just multiply this by however much time. That dot there is just multiplication. Time is not a vector, so it's not a dot product. It's just a vector times the scalar. And we drop that just to avoid potential confusion later. I don't need a subscript for the time like I wrote over here because it's the same time. From Newton's second law, what is that? Let's assume this is the total force, that these are the only two objects in this universe. What is force equal to?
Mass and acceleration.
And again, that would have been really cool if everyone had done that in unison. That would have been. And recorded too. I could have shown that one again and again. So that's the mass of A times the acceleration of A times time equals the mass of negative mass of B times the acceleration of B times time. What is acceleration times time? I heard somebody say something.
Is it speed? No, don't say, don't.
I will say that I have a vector times a scalar, so my answer will be a vector. Let's just do an example here. Let's say that I'm accelerating 5 meters per second squared in some positive direction, and I do it for 3 seconds.
Meters per second, so seconds would cancel out, it's velocity.
You now have seen the ballpark. Let's see if we can get inside it.
Is it displacement?
No, no, you turned your back at the ballpark now. Well, I stand corrected. No, you're still sort of looking at it. You sort of get it in the periphery. You could find this. Well, no, that can't. You turned your back on it.
Okay.
There's an important piece of information you're missing to find displacement.
Travel.
No, not. If I tell you acceleration time, assuming that these are the two things that you have. Dylan came up with 15 meters per second and then concluded that it was velocity. Couldn't be a vector, speed's a scalar.
Is it final velocity?
Not final velocity. You have your foot in the air, trying to decide if you're gonna walk towards the stadium or not, or ballpark. What does acceleration tell us?
How fast?
Change in velocity.
It's the rate at which velocity changes. Acceleration times time is not velocity itself, it's the change in velocity. So this is mass of A times the change in velocity of A is equal to the negative mass of B times the change in velocity of B. Let's not forget those vector signs. Change. If I got two numbers, how do I find the change?
Subtract them from each other.
Subtract what?
Find the change.
Yeah.
You subtract the initial from the final.
Okay. So I get mass of A times V final minus V initial of A is equal to negative mass of B times V final of B minus V initial of B. And now I'm going to distribute, because what the heck, why not? So I have, and this next line I'm about to write is the biggest pain. We're going to simplify it right after it. So I have mass of A times V final A minus mass of A V initial A is equal to negative mass of B V final B plus mass of B V initial B. Now physicists get to this point and they're thinking, that is too much writing to do. Let's see if we can simplify it. Because I got this MV showing up again and again, so let's just come up with a letter to represent that. And of course they pick the letter P. So this just becomes P final A minus P initial A is equal to negative P final B plus P initial B.
That's not P as in power P.
That is not P as in power. No.
Okay.
Power is a capital P, and this is clearly a lowercase p. No, this is, P for power is not a vector. That's one way to tell the difference.
All right.
And so now, well, I've got this final and final and initial. Let's get all the initials on one side, all the finals on the other. So I'm going to add PIA to both sides and add PFB to both sides. So on the left-hand side, I get P final. I'm going to switch the order of my subscripts there to something I usually do, PA final plus PB final is equal to PA initial plus PB initial. This equation, as simple as it is, gets physicists' hearts all aflutter. Because what we have here is whatever this P is, I have these two objects, the total beforehand is equal to the total afterwards. It does not matter what happens in the middle, if I know what happens beforehand, I know my total afterwards. This is conservation in physics. Conservation in physics means my total at one point is equal to my total at another point. And so the general notation, obviously big P, little p, it's very difficult to differentiate. This next thing I'm going to write is a big P. Typically written the other way around, but When you see the big letter P, that represents the total. This lowercase p is for an individual object. And that might be one of the few times that I will very hopefully clearly write the difference between a capital and a lowercase p. At this point, I will generally write a lowercase p and just let the subscript speak whether it's a total or not. And this p has a name, and it is momentum. And writing farther and farther into the corner, making it harder and harder for.
It is a lowercase p. Allegedly.
Lowercase or uppercase, the p vector.
As long as it's the vector.
Yes, okay. There it is.
Why were you able to take time out of the equation at the beginning?
Then we would just end it up with Newton's third law again. I was trying to get to the fact that initial momentum equals final momentum. Momentum is conserved. So I take this marker. From our reference frame, what is its velocity right now?
It's 0.
What is its momentum right now?
0.
I drop it. As it's falling, is the momentum still 0? I just made the claim that my momentum's conserved, yet it seemed to somehow gain momentum.
It doesn't matter about the path. Is that where, because it's conservative?
Conservative, non-conservative, not involved here.
Okay.
Yeah, that's an energy thing.
Would you say the final momentum and the initial momentum are the same?
Yes, the
Okay.
total final equals the total initial, but as I fell, it didn't really seem that way. What canceled out? If this is true, and we physicists live by this, if this is true, well, maybe physicists are just kidding themselves. I hope not, because that would basically 100 years of physics wiped out in a second. As it falls, it gains momentum. But if that's true, there must be something which has going to cancel out with that momentum. Has to be a momentum in the other direction somewhere. Surprised you didn't feel it. All right, remember what we started with. We have these two objects that are interacting with each other. What was the cause of it falling? What object caused this thing to fall? From what was the source of that gravitational pull?
The ground.
So, as it fell, what else had to have happened? Because my total still has to be 0.
It pulled the earth to it.
Yes, the Earth moved. Its mass, the mass of the Earth is so incredibly huge that the velocity doesn't have to be much. And I've gone through the calculations. If I drop I think if I jumped off the table, the Earth moves basically the size of a nucleus of an atom. So, but in the situation right here, how many of you felt the Earth move as the marker fell? So we differentiate these two situations here. Because the first situation, I had the two objects colliding. Very clearly, I have two objects. Everything is self-contained. That is known as a closed system. And so if I took into account everything involved, it's a closed system. There are no outside influences. All the forces acting on the objects are by other objects that I'm taking into account. An open system is one where I don't take it into account. So in the case of the marker, when it fell, I could count that as an open system if all I did was look at the marker. It's a closed system if I took into account the marker and the Earth, both. In a closed system, the total initial momentum equals the total final momentum. In an open system, momentum is going to change because there's an outside influence causing this change, as in the case of the marker falling.
So said for closed system, there's no outside influence.
Closed system, yeah, no, in there, no outside influence. Well, if I follow the chain of thought here, on the left-hand side, I have the force on A times time. I don't switch sides till I get over here, till I get to this step. Well, this, if we look at just that piece, I haven't switched sides yet, that's still force times time. That's my change in momentum right there, that's change in momentum of A. Tracing it back, that change in momentum of A is just equal to force times time. So in an open system, force times time is equal to the change in momentum. And of course, physicists can't let it go without giving a name to this, besides change in momentum. Now it's possible this is the most obscure clue. When someone suddenly buys you flowers, that is called wow, I usually get comments like, nice. Perfume commercial from the 70s, come on. We all remember those. Impulse. And you can find the Impulse commercial on YouTube. I don't think I included it in the link for 110. I don't think I did it for in the other one. So impulse, it is a vector. It's the change in momentum or it's force times time. If you're given a question and asked to find the impulse, which one do you use? Whichever one you have information for. If you're given mass and the initial and final velocities, I'm doing this. If you're given force and time, you're doing this. Questions to hear? All right, let's just do a little simple little problem here. A 3 kilogram object moving to the right at 4 meters per second. I have a, let's say 6 kilogram object moving to the left at 1 meter per second. They are going to collide and stick together. What is the final velocity? If we were using Newton's second law to do this, it becomes a lot more difficult because they start out with absolutely no force on each other. They touch, so the force goes from 0 to something maximum, and then as they separate, it goes back to 0 again. So the force is not constant, which makes doing F equals ma a lot more difficult without with inconstant force. Varying force, probably more modern. Inconstant for you Shakespeare fans. This is the power of momentum, is the fact that I don't care about what happens while they're interacting. If I know what's going on before, I know what goes on afterwards. This is a closed system because I have mentioned nothing else in this problem other than these two objects. Do not assume anything else involved. So first thing, what is the momentum of the mass here? So I'm going to label this as P3 initial. What is the momentum of this object?
I missed what you said.
Oh, what is the momentum of the 3 kilogram object before the collision?
12.
Give me the whole thing.
12
Meters per
meters
second.
per second.
If you're stopping there, then you've left the word off.
12 meters per second to the right.
Sorry?
12 meters per second to the right. Or
The issue with units.
Is it 12 meters per second squared?
No.
No, it's Is it newtons?
12 Newton.
Newtons?
All right, so let's take a look at doing the math here since people are dancing around it.
Kilograms per meter.
So it's-
Yeah, it's newtons,
I
right?
was thinking.
Mass of 3 times V3 initial, which is 3 kilograms times 4 meters per second. So 12, I'm good with the 12. If I look at the units, I got a kilogram here and a meter per second. And I'm multiplying. It's a kilogram meter per second.
And that's Newtons too,
That's
right?
good.
No, a Newton is a kilogram meter per second squared.
Oh.
Ah, we were close.
Newton, kilogram meter per second squared. A joule, kilogram meter squared per second squared. A watt is a kilogram meter squared per second cubed. And kilogram meter per second has no single word name. Because the powers that be sat around and said, we don't want to honor anybody.
Is it not Newton?
I was confused.
Newton's got an extra second in there. Now, if I take my Newton there, if I take my kilogram meter per second squared and multiply times a second, that would cancel out, this works. So this would actually, could also be 12 Newton seconds. Which also can be gleaned from this formula right here, because the units have to balance. Units of momentum have to be the units of force times the unit of time. So 12 Newton seconds also works. And that is a 12 and not the letter R. All right, so now, what is the momentum? Oh, questions?
Is it, for work, is it the seconds cubed?
Watt, that's a watt, not work.
Oh.
Yeah, we run out of letters. That is seconds cubed.
I had a question.
Oh, is momentum usually